Hello everyone. Uh, let's start our next chapter, and in this chapter, we will talk about the universe. We will look at the basic introduction to the universe, and doing so, let's start with what we see in the night sky. As we know, the night sky is the humanity's first window to the universe. Uh, ancient of ancient civilization uh, observed these patterns of stars and planets and used those patterns to create calendars, navigation systems, and even early scientific ideas about cosmos. So we can say uh, we have been observing the night sky since the times of ancient civilization. When we look at the sky, we see different different objects. First, we have stars. Stars appear as tiny point source of light because they are so far away. They only look like a tiny point light source, and stars also looks like they are twinkling, and their twinkling is caused by atmospheric turbulence which bends the starlight as it passes through Earth's atmosphere because of uh, the change in density caused by the turbulence of air. As we know, the density change in density will change the refraction index of the matter, and as the air is turbulent, the refraction rate is changing, so we will see these point sources as a twinkling light source. In contrast, planets are close to us compared to all these stars, and this planet will uh, look like a disk instead of just a point source, and planets shine steadily because they reflect sunlight, and also, as we said, they look like a small disk, not just a point. And since they look like a disk, where we have a higher surface area compared to what we see star as, the turbulence effect is less noticeable. So we can say planets don't twinkle much, though on windy nights when the air turbulence is high, they may simmer slightly. And on top of stars and planets, we also see objects like moon or nebula, and these are called extended source. Uh, Extended sources, since they are visible, since they have both visible shape and size. And this observation of night sky form the foundation of astronomy. Let's talk about the universe now. The universe is everything that exists. uh, Space, time, matter, energy, and the vast emptiness between these galaxies. In other words, a universe contains all stars, planets, galaxies, all form of energies, radiations, and dark matters. The age of the universe is estimated to be 13.8 billion years, and this estimation is based on the evidence from cosmic microwave background radiation present in the universe, as well as the expansion rate of the galaxies. Uh, Furthermore, images from space telescopes like Hubble Space Telescope, especially the ultra deep field images, reveal that even a tiny patch we see. For example, here we can see even a tiny patch of sky contains thousands of galaxies, thousand of galaxies, and each of these galaxies contains billions of stars. This shows the unimaginable scale and richness of our cosmos. We can see here in this video, this is a zoom out video. It starts with a small area, and then we can see it keeps going on, showing us the scale of the universe. As we say, the universe, the scale of the universe, to describe this cosmic distances, normal measurement units like kilometers or miles become impractical. So astronomers use different distance measurement like light year and astronomical unit. A light year uh, a light year is the distance traveled by light in a vacuum in 1 year, and the light year is approximately about 9.5 trillion kilometer. And we also use astronomical unit, and this astronomical unit is the average distance between sun and earth, and this astronomical unit is approximately equal to 150 million kilometer. This astronomical unit is what we will use generally when we are talking about solar system, and otherwise we will generally use light years to represent the distance between galaxies, stars, etc. And because light takes time to travel, looking at a star, for example, 1 light year away means seeing it as it was 1 year ago. In other words, we can say that telescopes are a kind of time machine. When we observe deep space, we are basically looking into the past, because the light has been traveling for example, if it was 1 light year, light was traveling for 1 year. So the star we are seeing is basically from 1 year before. And we talked about different objects in the night sky, and to locate these objects in the sky, astronomers imagine a celestial sphere. Here we can see in the image celestial sphere, and it is an imaginary enormous size sphere surrounding the earth. And the celestial poles of this celestial spheres align with this pole of earth, as well as this equator also aligns with Earth's equator. Stars and planets are projected into this sphere, helping us define their position in a clear and systematic way from the earth, any location on the earth. This model of celestial sphere simplifies sky mapping. even though the stars aren't really attached to this sphere. By projecting these objects we see in night sky into the celestial sphere, we are able to map the night sky. And this celestial sphere allows allows a consistent positional measurement from any location on the earth. And as we said, this celestial sphere is used to locate the position of these objects. The position on the celestial sphere are described using two coordinates. First, we have altitude. Altitude is basically the angle from this plane where the observer is at, known as horizon. So the altitude is the angle between this object. Sorry, altitude is the angle above this horizon, and horizon is basically the plane and that observer is at. Or we can say if we look back here, it's basically this plane. And then we have this azimuth, which is the angle all around the horizon. So using altitude and azimuth, we can position the objects in the sky. And we also have this celestial meridian, and this celestial meridian runs north to south through the observer's location. Through the north, it runs north to south through the zenith, and this zenith is the position at the very top above the observer's position. And we also have a point called nadir at the bottom of the bottom in the opposite side of the zenith, covered by this meridian circle. And because earth rotates, celestial object appears to rise and set in the west. All these objects seem to rotate around celestial pole. This is why we see circular stars trail in, like if we are taking a long exposure or night photos. The rotation of earth is what causes for us to see all these objects rise and set at certain interval of time. And let's talk about the stars and their properties and characteristics. Stars are self-luminous objects. They are a sphere of hot gases, and primarily the stars are made up of hydrogen and helium. In the core of a star, nuclear fusion converts hydrogen atoms into helium atoms, and this nuclear fusion releases tremendous amount of energy as light and heat. Additionally, since they are highly dense sphere of hot gases, the gravity is very strong, and this gravity pulls all these matters inward, while this energy from fusion pressure pushes this matter outward, and this inward pull from gravity and outward push from fusion balances each other, keeping the star stable for most of their lives. And the key characteristics of a star are mass and the color. The mass determines the star's size, brightness, temperature, as well as their lifetime. And the color of the star also tells us about the temperature of the star. Uh, uh, the color depends on the surface temperature, as we know from previous chapter where we talk about black body radiation. So as we know, black body radiation says that the color only depends on the temperature of the surface. We can looking at the star's color, we can tell about the temperature of the stars. uh, Cooler stars appear red, while hotter star will appear blue. And the mass and size of stars are defined uh, relative to the sun's reference. The size of a star is generally represented in solar radii, which is the reference to sun's radius, and the mass of the stars are generally represented in solar mass, which is the basically the reference with sun's mass. In the image here, uh, this is a region, star forming region, meaning there are materials that are prone to form stars. And this image was taken by European Space Agency using Hubble Space Telescope. And we should also know that stars vary in brightness as well as on their composition. However, all these stars with a different brightness and composition is what gives this light on this uh, cosmos. Now, when we are talking about stars, we should definitely talk about the stars, our stars, and our star is called the sun. Our sun is an average medium-sized star, about 5 billion years old, and it is also considered a middle age star. Uh, and the sun is stable, uh, is in stable condition because of hydrogen in its core fusing into helium, creating an outward pressure that balances the inward pull of gravity. And we can say the sun is a stable star. uh, Eventually, when the hydrogen runs out, the core will contract and heat up, causing the sun's outer layers to expand into red giant. So this outer layer will expand into red giants. The sun still has enough hydrogen for another 5 billion years before it reaches the state of a red giant. And eventually after millions of years, millions and billions of years, the sun will shed its outer layers and change from red giant uh, and leave behind a white dwarf. Eventually uh, the sun will convert into white dwarf, and not the sun. Generally the typical stars, uh, or we can say mid-sized stars, will eventually convert into white dwarf. White dwarf is nothing but a hot dense remnant about the size of earth. So they are hot dense the the brightness of the stars depends on uh, the luminosity size and the distance, how distance between the stars and earth. And when we observe stars, and the luminosity, or the amount of light, the amount of light produced by the star is called luminosity, and the brightness of the stars depends on this luminosity, as well as the size of the stars. uh, Larger stars have more surface area to emit light, uh, or in other words, larger stars have higher luminosity, and we can see the relation. The luminosity is proportional to the square of radius and fourth power of temperature. And the brightness of stars also depends on the distance, this between the observer and the star, and the relation is that brightness decreases with distance, with an increase in distance following the inverse square law. If a star is twice as far, it appears 4 times dimmer. We can also see that representation in the image here. If the candle source is close to us, we see a brighter light source here. As the candle goes farther away from us, we see it dimmer and dimmer. Is the same case with the stars. If the stars are close to us, we will see them shine brighter. As the stars are if as the distance increases, we see them dimmer and dimmer. The brightness of stars is represented in a measurement called a magnitude, and this magnitude does not have any units, and the smaller the magnitude, the brighter the stars are. And these units of brightness are of three types: apparent magnitude, absolute magnitude, and sometimes you will also see in terms of luminosity. Apparent magnitude is defined as how bright a star appears from Earth. So basically, this apparent magnitude is how we quantify the brightness as we see the star from the Earth's surface. A first magnitude star is about 100 times brighter than 6 magnitude star. And this apparent magnitude is a logarithmic base unit, and we will have uni- five uniformly distributed lines between first and sixth magnitude first and sixth magnitude. And then we have absolute magnitude. The brightness of a star would have if the absolute magnitude is the brightness a star would have if placed 10 parsecs away. So basically brightness adjusted to a standard distance of 10 parsec, and this is a new unit, so we should define a parsec. So 1 parsecs is equals to 3.26 light year. So basically we can say a brightness adjusted to a standard distance of 32.6 light years. For example, here we can see if the sun's apparent magnitude is minus 26.7 and absolute magnitude is 4.8, and the luminosity is basically the total energy emitted per second, often expressed in solar luminosity, and again this is with reference to sun, meaning the sun's luminosity is 1 solar luminosity, and this is directly related to absolute magnitude. And we can see here in image, in the image in the right, we can see so this column here is how many stars visible from the Earth's surface, and it's giving us the magnitude that we see the brightness of. So we will see around 1 stars that's of a magnitude -1, around 3 stars with magnitude 0, 80 stars plus 1, and so on, around 3500 stars with magnitude of 6. And as we say, sun looks really bright because it has very small magnitude of -26. A full moon has a magnitude of -12.5, and the values reduces as the stars are dimmer. And if you want to look at how what we see in the night skies in more detail, please refer to this website. They have a lot of information in their website. And the color the color of stars are really important when we characterize the stars. A star's color reveals its surface temperature, like we said before, based on the black body radiation. Blue star are generally the hottest stars with a temperature nearly about 30,000 Kelvin. We can see here, and since this is a black body radiation case, we can see it's based on the wavelength, and as the wavelength increases it becomes more bluer, and as the wavelength of the light produced by the stars reduces, they shift to red color. So if you look at this graph, the wavelength is smaller in this direction and larger in that direction. And yellow or white stars are medium temperature stars. For example, sun is a medium star, and the surface temperature of sun is around 6000 Kelvin. And then the red stars are the coolest star, and the approximate temperature of a red stars is around 300 three, around 3333 Kelvin. And an example of a red star is Betelgeuse star, and example of blue star are Rigel and Deneb stars. And astronomers classify stars using a sequence OBAFGKM from hottest to coolest star. And the HR diagram, Hertzsprung-Russell diagram, plots stars absolute magnitude of brightness versus temperature, and it shows us all these bubble plots of different stars and their effective temperature and luminosity in a single diagram. And this HR diagrams reveal this distinct regions. For example, main sequence. Here we can see this this region is called main sequence, where most of the stars lie, and in this main sequence these stars are in stable condition, and their power source is hydrogen fusion, and they are in stable conditions. Then we have this giants and supergiants. uh, Giants and supergiants region, and these are bright red but cool stars, and they are expanding in sizes, and they are called giants or supergiants region. And then we have white dwarfs, and these white dwarfs are hot but a faint remnant of dead stars. So basically HR diagrams gives us these different regions uh, of these objects. And this diagram is like a roadmap of stellar evolution, showing how stars change as they age. Now let's talk about life cycle of a star. Stars form in the birth of stars is from a molecular cloud, and this molecular cloud is cold dense region of gas and dust. And this molecular clouds are a type of nebula. And as we said, as we said, these molecular clouds are cold and dense, cold and dense region of gas and dust. The density of the high density of this gas creates even high density pockets, and some of these pockets will collide with each other uh, because of the gravity, and these clumps will start combining with each other, and they start heating up as they collide. And the gravity also pulls them inside, because there's no fusion yet to balance the gravity. This hot and dense sorry this dense air cloud collapse because of the gravity. and this collapse will heat up these gases. So packet collides with each other, collects more matter, that increases the mass, and as the mass increases, gravitational force also increases, and this gravitational forces will collapse the uh, gases causing a high temperature, and this high temperature will lead a development of a proto star, and basically that's a baby star. A baby star, a proto star is a baby star glowing from gravitational energy. And when the temperature, as the process further, when the temperature reaches millions of degrees, nuclear fusion will begin, and the star will be is stable because of the balance between the force caused by gravitation, and the force caused by nuclear fusion from between hydrogen atoms to form helium atoms, and this creates a stable star. And when a star exhausts, the hydrogen present in the star's fusion slows and the core will contract, and because there's not enough energy to balance the force uh, force of gravity, eventually this core will contract, and based on the mass of the star, the they will form different objects. For low mass stars like the sun, uh, the outer layer will expand, as we said. The outer layer will puff off and uh, convert into red giant stars, and eventually this outer layer that was puffed up will shed out of this red giant, and they will form a planetary nebula. And the since these outer layers are out of are this are shaded from this core will be converted into white white dwarf, and eventually these white dwarfs will cool slowly, and these white dwarfs are uh, approximately earth sized, and eventually they will cool in billions of years. And then this is the case for low mass stars. For high mass stars, fusion the it will continue fusing, the fusion process from helium to carbon, uh, or sorry, for low mass stars, the fusion is from hydrogen to helium, but for high mass stars, the fusion will continue beyond carbon, oxygen, neon, magnesium, and up to iron. So it does not stop from hydrogen to helium. This big high mass stars will fuse up to iron, and then collapse and explode as a supernova, and the core remnant becomes a neutron star, or if they are massive enough, they will form a black hole, and this that's recycle heavy elements into space, and this is what will will form a seed for new stars as well as planets. And we can summarize the stellar evolution. Like we said, low mass stars will ultimately form a white dwarf. Medium mass will form a neutron star, and if they are massive enough, they will form a supernova, black hole, where the collapse, the black hole, in the black hole, the collapse is so strong that even light cannot escape from the black hole. And this is also summarized here. First we have this molecular cloud, and then from a small star called protostar, red giant, planetary nebula, and then white dwarf. And for larger star, red supergiant, then convert into supernova, and if they are large enough, and it will form black hole, otherwise neutron star. And let's talk about larger scale structures. As we know, stars rarely exist alone. Stars exist in either binary systems or clusters of stars. So the binary system is two stars orbiting each other, or two stars orbiting a common center. And then we have star clusters, group of hundreds or thousands of stars formed together. And then we also have galaxies. Galaxies are basically a collection of vast collection of billions of stars. So galaxy, in a single galaxy there will be billions of stars. And on top of when we are talking about large scale structures, we also have cluster or supercluster of galaxies. So basically collection of galaxies. Our own galaxy, and the galaxy we are in, is called the Milky Way galaxy. And this Milky Way galaxy is part of massive supercluster called, so our galaxy is Milky Way galaxy. This is a supercluster. Our Milky Way galaxy lies in a supercluster called, Laniakea. So this is I. And here we can see this is a Laniakea supercluster, image of a Laniakea supercluster, and this includes more than 100,000 of galaxies. As we say, one single galaxy can have a billions of stars, and we are talking about 100,000 estimated galaxies. So we are talking about trillions of stars. Now let's talk about our galaxy, the Milky Way galaxy. The Milky Way galaxy is a spiral galaxy about 100,000 light years across and around 100,000 light years across and around 1,000 light year thick. And the Milky Way galaxy contains roughly around 200 billion stars. And as we said, this is the, the galaxy is like a disk with spiral arms, and the Milky Way galaxy has a galactic nucleus. We can say this is a galactic nucleus, which is a dense central region which looks like a disk with a spiral arm, and this spiral arm is rich in gas and dust where new stars will form. So this spiral section is rich in star making objects, and it also contains halo, which contains old stars as well as dark matters. And our solar systems, if you see here, our solar system is somewhere here in this Milky Way galaxy. It lies about 1/3 of the way from the galactic center. It's at around 1/3, and about 90% of the Milky Way galaxy's mass is just a dark matter, and this dark matter are unseen but detectable by its gravity. That's where all these different theories in about the universe comes. For example, uh, relativity and other stuff. So the around 90% of mass are invisible dark matter. And if we look beyond the Milky Way, there are billions of other galaxies. Uh, those galaxies are spiral, elliptical, as well as irregular in shape. The astronomer Edwin Hubble in 1920s discovered that distant galaxies are moving away from us. So when we see a galaxy, those galaxies are always moving away from us. The farther away a galaxy is, the faster it recedes from us, and this principle is known as Hubble's law. And this redshift of light is what we talked about. Redshift in our light chapter, where we say if a star is moving away from us, we will see redshift. We will observe and redshift, and this redshift of light is evidence that the universe is constantly universe is expanding, meaning when we say our universe is expanding, we are saying space itself is stretching. Space itself is stretching. Not just galaxy moving away, the space on itself is stretching. And this discovery that universe on itself is expanding led to the modern model of evolving universe. And now when we are talking about the expansion of universe, we should definitely talk about the Big Bang. The Big Bang theory describes the beginning of the universe, and based on the background radiation information we see in universe, the universe is approximately 13.8 billion year And the Big Bang Theory describes that the beginning of the universe about 13.8 years ago in an extremely hot, dense state from a point source, and the evidence for a Big Bang for the Big Bang are the cosmic microwave background radiation present in the atmosphere, sorry, not atmosphere, present in the space, and this is the afterglow of creation. And then we also talked about the redshift of galaxy, and this redshift of galaxies shows that the universe is constantly expanding, supporting the Big Bang theory, starting from a point and expanding expanding over the time. And the fact that there are abundance of light elements, for example hydrogen, helium, lithium, etc., also supports the Big Bang theory. And as we said, space itself has been expanding ever since the Big Bang. Yeah, not just galaxy flying through space, but space itself is stretching between them. And the universe continues to evolve, and we are just a part of a grand history.